Welcome to the Optimus Process Solutions webinar series. This is your host, Tom Zhang, introducing our guest speaker today, Glenn Hanson from Industrial Kiln and Dry Group. Glenn graduated from University of Wisconsin Green Bay, and yes, he is a cheesehead. His degree is in environmental sciences with a focus on waste management. Glenn has been in the pulp and paper industry for 25 plus years, concentrating mainly in the lime recovery process. Without further ado, welcome, Glenn.
Thank you, Tom. Certainly appreciate it. We will be talking today more in depth about the Kraft Pulp Mill lime kiln process and operations. Basic outline will be a process overview, the types and designs of lime kiln systems, improving efficiency in lime kiln systems, and optimizing operation. The lime kiln is an important part of the kraft recovery process, and it's important to remember that it is an interlocked process in which all of the other things within the kraft process will affect it. So making good lime will result in good white liquor going to the digester, good operations through the recovery boiler, and good green liquor coming back to the recausticizing plant. The kiln is an integral part of recausticizing. What you're doing with the kiln is taking the washed mud, running it into the kiln, recalcining it so that it can be reused in the slaker, which then goes to the causticizers, producing white liquor, and again, lime mud to be recalcined and reused again. The purpose of a lime recovery kiln is to regenerate or recover lime from calcium carbonate or lime mud. It saves the purchase of fresh lime and saves the cost of lime disposal. The kiln itself is a countercurrent type heat exchanger. The wet mud is fed at one end, dried, preheated, and then calcined. The process requires heat, which is provided by the burner at the opposite end. The basic reactions that are occurring are drying of the wet mud, in which we are vaporizing the water off, calcining of the dry mud, converting it from calcium carbonate, CaCO3, to CaO, and the combustion of the fuels to generate the heat for the process. Basic reactions again, in the kiln, we are heating it up to calcining, thereby removing the carbon dioxide from the lime, converting it to CaO. The lime is then fed to the slaker, in which it mixes with water and becomes hydrated lime. The hydrated lime then reacts with the green liquor to produce a solution of white liquor and a solid of lime mud, which is then again washed and run through the kiln. The calcining reaction itself, again, calcium carbonate is transferred to lime and produces carbon dioxide. This occurs rapidly at about 1470 degrees. The rate increases with temperature and decreases with CO2 partial pressure. It is reversible at lower temperatures. So there is a point within the kiln itself at which that conversion is occurring, and that area can move around in the kiln based on temperature profile. Part of the kraft mill process may involve the incineration of foul gases such as NCGs, SOGs, or other dilute sources. You may have problems with high TRS emissions when you are trying to use these materials within the kiln to oxidize them, to collect them and oxidize them. The problem with foul gas oxidation with NCGs is it aggravates kiln ringing. You can have variations in fuel and water content affecting the flame pattern and or temperature. You may also have the formation of a hard calcium sulfate that causes ringing. The amount of NCGs that you can fire in a kiln has limits. Dilute NCG volumes can limit secondary airflow. This is especially critical on kilns that are using coolers. The water content can cool the flame excessively. This is just a look at typical lances that are set up because NCGs are introduced separately from the main burner. This is to allow the main burner to provide the heat that's needed and the NCGs to not directly affect the combustion process. If you are operating a kiln and you are firing NCGs and you get into a situation in which you have TRS emissions issues, one way to check and determine where that TRS is being generated or where it's coming from is to actually go in and increase the excess oxygen coming from the kiln by opening the damper or increasing the ID fan speed. If the TRS level goes down at that point, the TRS is from the fuel and or the NCGs not being fully combusted or oxidized. And you need to look at the burner system and or the NCG lances to determine if there's a problem. If the TRS stays up or stays the same or goes up, the TRS is coming in with the kiln feed. Need to check your mud washing and pre-coat filter operations. This is a quick look at the exterior of a lime kiln, very basic, without coolers, etc., showing where the mud comes from the pump, goes across the filter and into the kiln. Again, it's counter current, thereby meaning that the gases are being drawn through the kiln from the discharge end. The burner is producing the heat coming in, the secondary air is coming in from the hood, goes through the kiln, up to the ID fan, through a wet scrubber, and out the stack. The kiln is turned by a main drive, typically a gear and pinion type arrangement, and it's supported by tires that are run on support rollers or trunnion rollers. The older type designs are kilns that were without coolers. You were not recovering the heat from the product material. That is shown here. You basically ran the material through, it came out as a hot discharge, and then went to storage. Later on, product coolers were applied. The first coolers that were typically applied in lime recovery were satellite tube type coolers. What is happening here is that the hot material goes into the coolers. Secondary air is drawn by the ID fan up through the cooler ports and comes in as a preheated air, thereby recuperating those BTUs into the process. Product coolers cool the material to approximately 350 to 4 degrees. They preheat the secondary combustion air to about 550 to 650 degrees. It especially adds to efficiency of the overall operation. Typical designs of coolers that are available in the lime recovery industry include the traditional satellite tube type coolers, which are shown in the picture, concentric shell type coolers, which are known by names such as compacts or sector type, that look like additional shells wrapped around the kiln. And there are also separate grate style coolers now being used in lime recovery. In every case, you're trying to recover the heat from the product material, bringing it back in as preheated secondary air. This shows a schematic of a modernized kiln with coolers on it. What is shown here is typically satellite coolers. If it was a concentric shell type cooler, it would be in the same location as well. Some older kilns have been modernized with cyclones. The idea is to collect dust that would be normally going out with the exhaust gas stream before it goes through the ID fan and to the scrubber. This allows this dried, preheated material to be returned to the kiln rather than it be wetted and going through the mud cycle again. This adds to the overall efficiency of the operation. Most modern kilns are equipped with precipitators, electrostatic precipitators, are known as ESPs. This diagram shows the precipitator in which the off gas would go up to the precipitator, the dust would be collected and returned into the kiln, dry and preheated as well. The gas then goes through the ID fan. In many cases, a wet scrubber is there, but it's not for particulate control as much as for SO2 control. This shows a current design lime kiln with an external dryer. These have become pretty much the most popular design for new kilns that are being erected around the world. In this case, what happens is the mud is fed instead into the riser duct or the reactor, the external dryer. It is then lifted, and while it is being lifted, the heat in the off gas from the kiln dries and preheats the material. It then goes through a cyclone for separation and comes into the kiln completely dried and preheated. Typically, you go through a precipitator, which again collects any residual dust, returns it to the kiln dry, through the ID fan, through an SO2 scrubber, and out the stack. This shows the interior of a conventional or straight type lime kiln. This is the critical difference between an LMD style kiln versus what we would call a conventional or straight kiln. To actually do the drying and preheating, a conventional straight kiln is equipped with a series of chains. LMD type kilns or external dryer type kilns are not equipped with chain systems. Time and temperature balance through a kiln is critical as well. It's a cooking process. Typically, you're looking for approximately 150 minutes in overall retention. This gives you a reasonable kiln length for the process to occur. The kiln rotation is optimized for effective bed depth and retention time while minimizing dust losses. You are targeting approximately a 1900 degree burning zone temperature, yielding a slow cook and long refractory life. You're looking for what is called a good soft burn lime. This is not to say a high residual carbonate, but what you're allowing for is a lime that is not too hard to react and has the right amount of residual carbonate. The effective evolution of CO2 from the pellets as they're coming down the kiln gives you a good reactive lime with good mud particle formation and settling. We have shown here the equation for retention time in a conventional kiln. Basic mass balance as you work your way through the kiln, you have to take into account the dust loss that is coming out of the kiln and the availability that you are looking for. In general, you are looking at approximately double the amount of feed coming in to produce for example, 2 pounds to produce 1 pound of kiln product. Kilns are sized for production rate. They must have adequate open area to control gas velocities, support the refractory, have heat transfer without overheating the material. Internal volume factor is the key number that's looked at. Normally, kiln volumes inside the refractory per short ton of kiln production per day are typically 60 to 85. Kiln sizing, also kiln geometry, comes into play. Typical length to diameter ratio is somewhere between 25 to 30 to 1. Kilns equipped with external dryer systems or flash dryers are typically on the lower range. Straight or conventional kilns are typically on the higher range. This is important when you look at this for upgrade or retrofit potential with an existing kiln. The mechanical design of the kiln follows the process design. The number, the size, the locations of supports, the drive sizing are all very important. They are designed for a specific mass to be rotating. If there is significant additional amount of material that is going to be put in or a change in refractory, this must be considered and reviewed for a retrofit and incorporated with a new system. General process philosophy of lime recovery is to convert the lime mud in a cooking way. You must have a good balance between time and temperature. Too long a time, not efficient. Too high a temperature, you will not have good product. You want to prevent kiln dust loss. In other words, you do not want your feed coming out as dust loss. You want to dry early in the process, have a long and even preheat, giving a good prepped material coming into the burning zone for even calcination. You focus the heat input towards calcination and production and maximize your excess heat recovery. An optimum chain system or external dryer design is important for this. Recover product heat through product coolers and minimize shell radiation losses by using insulated refractory. The kiln is broken up into 3 basic zones. The drying zone will vary with the feed moisture and feed rate. The burning zone is typically considered to be 7.5 to 8 times the kiln's diameter in length from the discharge end. The middle area is known as the preheat or intermediate zone. Looking at general kiln production and efficiency, older kilns were often oversized, 100 plus cubic feet per ton per day, relative heat rates of 9 million BTU per ton of lime or more, and fairly high energy consumption at 67 kilowatt hours per short ton. As time went on and different things were applied for retrofits to increase efficiency, those factors began to drop. It became typical to see 73 to 78 cubic foot per ton, 8.4 million BTU, 63 kilowatt hours. New, longer kilns with high efficiency internals, product coolers, and precipitators can go as low as 70 to 75 cubic feet per ton per day, relative heat of about 7.3 million BTU, and electric power consumption of around 45 kilowatt hours per short ton. External dryer equipped systems allow for much bigger throughput in the kiln, but are slightly less efficient. We will now look at a general benchmark kiln. We've run a heat mass balance in this case. We have picked a kiln with no coolers, no cyclone, and no precipitator. There are a number of these, especially in the North American area. What we will do is look at different factors to be able to increase the efficiency and or production of these units. The lime kiln heat rate is a measure of the energy efficiency. The units are million BTU per ton of lime or gigajoules per ton of lime. It is often stated as million BTUs per ton of product. Typical range is anywhere from 7.3 to 10 million BTU per ton, or 8.4 to 11.6 gigajoules per ton. Obviously, lower is better. Looking at our sample kiln with our basic calculation or heat mass balance in there, contributions or needs for the heat rate and the fraction that are coming in, and looking at things that can help increase that efficiency, calcination makes up 32% of what is needed. There is nothing that we can do here. We are trying to convert the calcium carbonate over to calcium oxide, so being more efficient there is not possible. Drying, it is possible in this case to increase mud solids, thereby not needing as much heat to dry out the mud. Exit gas, if you can retain some of the temperature in and run at a lower exit gas temperature, you can again gain some efficiency in this case. Shell losses, or heat lost out through the shell, can be reduced using insulated refractory systems that are available. Heat lost with the product, which typically makes up 11% on a kiln without product coolers, can be gained, or you can gain efficiency in this case by adding product coolers. Dust losses can be improved as well. One of the things to look at in a conventional kiln system in this case is improving chain system design. Some of the major things that can be done for heat rate improvements are the addition of coolers, for example. In the case looking at our base kiln that we have defined, you can see that what has happened is we have reduced the product temperature dramatically by the addition of the coolers, which thereby, with that recovered heat, allows us to significantly reduce the amount of fuel that we are putting into the kiln, giving us an overall savings of approximately 9.6% when comparing just that factor. If we can increase the dry solids, the mud dry solids coming off of the pre-coat filter and going into the kiln, in the case that we are showing of approximately 5%, you will see as well that what we have been able to do is decrease the amount of fuel that is being put in. This gives us a 7.2% increase in efficiency. The addition of a Cyclone or a multiple tube type dust collector and return of that material dried and preheated to the kiln will actually help in several ways. One of the ways is that dust loss is not a loss from the system anymore, so you actually can feed less mud and still get the same production out of it. You also are actually getting less tonnage lost as dust. This allows you to get a situation in which you will see a savings of approximately 4.8% overall. Looking now to refractory systems, if you look at going to an insulated type refractory system, our shell losses drop significantly. You can see in this case, we see approximately a 4.1% reduction or savings, increase in efficiency. One of the other things that comes into play is variances in fuel. Because of the way that it combusts in the kiln, which has been covered in another of webinars through IKD, which you can look up online on our YouTube channel, we discuss the reasons why other fuels are more efficient, such as oil, petcoke, and others. In this case, we have a kiln that has changed over, using our base kiln, we have changed it over from natural gas to fuel oil. As you can see, the back end temperature drops significantly because of the radiant effects of the oil versus natural gas, giving us an approximate savings of 5.9%. So some of the longer term or higher capital projects that may be looked at to improve lime kiln performance are to improve the refractory system. If you do not have insulated refractory within your kiln, this is an opportunity to maintain BTUs within the system and increase efficiency. Switching fuels may also be an option. It's important to realize that cost differentials or direct cost differentials are only a part of the equation that you must look at. Natural gas, although it is less expensive currently, is not as emissive as fuel oil or petroleum coke. Thereby, it operates less efficiently. You can look at improving your chain system. If your chain system has not been maintained well over time, you are not getting as much efficiency out of it as possible. If it is an older design, you may want to look at completely retrofitting the chain system to increase your efficiency. Optimizing and/or changing your burner is also a possibility for increasing efficiency. It's possible that you have an older style burner that you are not able to get set up properly, and thereby you're not getting the correct or optimum heat release and heat transfer over to the material. Kiln control systems can be very beneficial. A kiln control system in an automated setting can actually look at parameters within the operation on a very rapid basis and make small, minute, or larger changes as needed to maintain the system operation within the rules base. Operators should not be concerned about a control system taking away their job. It actually is very beneficial to them because it allows them to look at other things or monitor other things while the kiln is being optimized without them having to pay very close attention to it. Another potential thing that can help, as was discussed, is a dry dust collection system, either a cyclone, a single stage cyclone, or a multiple tube type collection system can actually collect that dust, thereby returning it dried and preheated instead of it being re-wetted and having to be dried again in the kiln system. Some minor heat rate improvements that can be done. These are things that can, in some cases, be done on a daily basis. It's just a matter of looking at your operations and determining if you can apply these things in an effective manner to get the benefits. One thing to look at is the actual overall availability of your line. Availability is 100% minus the residual carbonate, minus the amount of inerts that are in the lime mud that is coming in. The inerts do not take part in the process. They do not take part in the process within the kiln, nor within the liquor cycle. So they're actually what would be considered a dead load. Within the kiln, these inerts must be heated up as well as the lime. So they are actually drawing away heat from the overall operation and decreasing your efficiency. If you can put in a purge, such as increasing the frequency of your dregs pre-coat filtering, the dregs pre-coat itself, if you can increase that frequency, or in some cases dump some mud and make up with a certain amount of fresh lime, you can get rid of those inerts and keep your availability up. In this case, what we are showing is increasing the availability 7% from 85 to 92. As you can see, you actually will save fuel in this case because you're actually producing more lime rather than total products. What you see as well is there is a reduction in the mud feed rate for the same actual lime production rate. This is because more of the material going through the system is lime rather than dead load materials that are inerts or non-process elements. Looking at optimizing the O2, excess O2 in your kiln operations is also very important. Excess O2 should be measured within the feed end of the kiln. If your probe location is in a duct or in the hood of the kiln, you are probably reading a lot of leakage air into the system. It's important to be reading excess oxygen within the kiln itself. This is an area that can be looked at and optimized. In our case here with our base kiln, what we have done is reduced the excess oxygen concentration from 3% to 2%. As you'll see, there's a corresponding feed end temperature reduction. Similar to what happens with non-process elements, an excessive amount of oxygen must be heated and it is not participating in the process. It's sort of a dead load as well. So you can see what we've been able to do here is reduce or increase our efficiency by 2.4% as well. So looking overall at some things to improve lime kiln performance, optimizing kiln excess oxygen concentration is important. It is controlled with the ID fan speed or damper or a combination of both. Excess oxygen concentration is not controlled with primary air. Primary air is mainly for the initial combustion and flame shaping. It should not be used as an oxygen control. 1 to 2% excess oxygen is normal. Each 1% drop typically represents 50 degrees reduction in back-end temperature. For kilns that are firing non-condensable gases or other foul gases, it is common to have to run a slightly higher excess oxygen range to compensate for the variances in flow of these foul gases. It's also important to establish, consistently test, and maintain kiln product residual carbonate. Residual carbonate is the one thing within a lime recovery kiln that is giving you an idea of how good you're doing, how good the conversion is from calcium carbonate to calcium oxide. How efficient are you converting that material? Typically 1 to 3% is a normal range. You need a test that the operator can respond to promptly. If samples are being taken daily, sent to the lab, and the response comes back a week later, this is not really a good situation. There are benchtop tests that can be done for residual carbonate, which will give an operator a good ability to respond to the situation to be able to control the residual carbonate range. Establish a range that provides good reactivity and settling. Target periodically test and control availability. Again, availability is important, but it is not the direct operating impact. So here we look at our base kiln in an optimized situation. We've looked at things like increasing solids off the pre-coat filter, possibly by something like adding a pre-coat cleaning shower, or possibly changing the type of material we are using, speed of the filter, etc. Different things can be done to increase this solids rate off the filter. We've also increased the availability, increased the purge out of the system, added a little bit more fresh lime to get that up to 92%. What that has done as well, and we've also decreased the feed-end oxygen. So you will see a corresponding decrease in feed-end temperature. Overall, we're going to use less fuel to make the same amount of lime that is going to be used in the recausticizing process. So as you can see, some things that you may be able to do on a day-to-day basis, not spending a significant amount of money, just paying closer attention to your operation, can reveal savings as high as 12.2%. Some general guidelines for good lime kiln operation. Change your feed rate slowly. Change in small increments of 5% or 10 gallons a minute, and allow the kiln to settle down. Very often, people are very concerned about inventories of mud, etc. What can happen in that particular case is a situation in which, if you do not allow the kiln to settle down, an operator cannot keep up and cannot make adjustments accordingly to maintain residual carbonate or product quality. What happens is these upsets then decrease the efficiency, and you make bad lime or higher residual carbonate lime, which results in actual more mud. So it's important to not only consider inventories, but consider effects on inventories if you jockey around too quickly or too fast with feed rate changes. Avoid large changes in kiln draft. This affects the temperature profile. Changes in temperature profile can significantly affect ringing within the kiln. Keep the kiln on the hot side. We're not saying just this side of smelting the kiln, but it is a lot easier to cool down a kiln than it is to heat it up. Maintain a constant firing rate while adjusting for temperature drifts and feed rate changes accordingly. Plan ahead. Visualize the consequences of the changes that you make and react accordingly and incrementally. You should use extreme caution during heat up and cool down periods. Use the OEM and or refractory supplier schedules when you're doing heat ups and cool downs. What that does in that case is allows you to rotate the kiln accordingly, thereby treating the refractory correctly. It allows the refractory to heat up and the shell to heat up together. If you try to start up too quickly and do not allow a long enough heat up, you will not soak the heat into the refractory, and you will spend much more time, and you will operate less efficiently for a period of time until that initial heat is within the refractory itself. You need to be very careful with upset and holding conditions. Note and monitor the conditions that you see, especially refractory temperatures. What you can do in these cases too is what we call bottling up the kiln. Turn the fuel rate down or off. Turn the ID fan down as low as possible to just barely draw a draft through the kiln, and hold it in that condition. That's the safest thing to do. Don't use shortcuts. Water introduction into a kiln, unless it's a complete emergency, can cause major problems. What can happen in a situation is that if you do put uncontrolled water into the feed end of the kiln, you may get into a situation where that water works its way down, goes through a buildup, and rushes down into the burning zone. Here you have hot, partially or completely calcined lime, which is then going to react with that water. You can get into issues as bad as steam explosions occurring, and you can't get out of the way fast enough. Quick heat ups are bad because they're difficult on the equipment overall, and especially the refractory. If you try and heat up too quickly, you are not allowing the shell itself to expand, nor allowing the refractory to expand within it. These are the most common times when kiln damage occurs. In upset conditions, remember to maintain kiln rotation to prevent shell distortion. You should always be checking the emergency drive on your kiln to make sure it is ready to go in any emergency situation. If you let a kiln sit too long with a hot load, it can take a banana-like shape, and it is difficult to get it back into its normal condition. Prevent the burning zone refractory from going above its rated temperature. Monitor it periodically to make sure that you are not overheating it or getting into a situation where it degrades. Maintain the kiln burners cooling or retract. For example, in a power failure situation, if primary air is all that you have going through the burner and that primary air fan is not connected to an emergency power source, that burner is also hanging out over that hotbed of material and can also warp or get distorted, get cracks, things like that. If you cannot maintain cooling of the burner itself, you should retract it for that period. Prevent rapid refractory heat up or cool down. I mentioned about bottling it up, cutting the draft of the combustion system is off. Also watch to limit exit gas temperature.
Well, thank you, Glenn, for this excellent presentation today. If anyone has questions for Glenn or would like for him to expand some more, please call the Optimus Process Solutions. We have a toll-free number. It's 844-880-5822. Again, it's 844-880-5822. Thank you.